And the question that was proposed is to explain significant digits. The student said, it sounds like a dumb question, but it's not. It's not a dumb question at all. But significant digits covers a great deal of territory. So we've got to pick some place to start. So I heard a shout out to start with addition, but I'm not sure that we want to start with addition until we talk about significant zeros. What would you like to start with? Zeros? Okay. So there are two formal rules. For significant zeros. And the first formal rule, there's a two-part rule and a one-part rule. Let's start with a two-part rule. Zeros are significant if they are between, the one-part rule is zeros are significant if they are between two significant digits. That's the one-part rule. Okay? Zeros are significant if they are between two significant digits. Now the assumption here, or the implication here, is that all non-zero digits are significant. All non-zero digits are significant. I kind of say that even though I don't have it written down that way with an asterisk, because there's kind of a caveat here. The assumption is for that. So that's an assumption about an assumption. The assumption is, ladies and gentlemen, that this would be this rule about all non-zero digits being significant is that the number you're looking at has already been handled properly for significant digits. Okay, so it's a measured number that's been measured properly. It's a calculated number that's been calculated and rounded properly. Okay, assuming that to be the case, then all non-zero digits are significant. And then for the zeros that are between significant digits are also significant. Okay? Then that's the one-part rule. The two-part rule is that digits that follow, meaning they are to the right of, digits that follow a decimal place and a non-zero digit are significant. Digits that follow, meaning they're to the right of, both a decimal place and a non-zero digit are significant. So that's the formal rules. Now I kind of like a couple of informal rules. If zeros are significant because they follow a non-zero digit and because they follow a decimal place, that's the two-part rule, then it follows from that leading zeros to the left of any non-zero digit are insignificant. And I like that one. You hear me use that sometimes. Leading zeros are not significant. Okay? Leading zeros are not significant. Trailing zeros, when there's a decimal place, are significant. That's another informal rule. Trailing zeros, when there's a decimal place, are significant. So that's the way I prefer to think about it. You can think about it any way you want to. All right, you use the formal rules, the informal rules. As long as you can get the significant digits right, that's what matters. Okay? Do you want some examples?
Yes.
Okay. So let's look at this number here, and let's call this grams of calcium chloride. And let's analyze this for the significant digits, see if we can figure out how many significant digits there are. So I want you to write this number down, and I want you to identify in writing how many significant digits there are here. Now we're assuming this number has been measured and the digits have been handled properly. That is to say, it's been rounded off properly if necessary. Well, if it's measured, it wouldn't be rounded off, but the digits have been handled properly in this measurement. Okay, Anton, how many significant digits do we have here in this number?
6.
I don't see 6. Can you explain?
Well, the 3 zeros after the decimal and before the 3 are significant.
These 3 right here are significant?
Yes.
No. Okay, let me try to explain. Using the informal rules, leading zeros are not significant. So these are leading zeros. They're to the left of any non-zero digits. Okay? Using the formal rules, we said that zeros are significant when they are between two significant digits. And since none of these are, there's nothing over here to tell you they're significant. Non-zero digits are significant, so this 0 here is significant. We said that trailing zeros are zeros that trail non-zero digits and the decimal place. Those are significant. So these are the significant digits. There are 5. These 3 over here are not going to be significant. Okay? So there's nothing wrong, remember, about being wrong. Nothing wrong about being wrong. Okay? It's not addressing the problem. It's not learning from your mistakes that's the problem. Okay? Everybody's going to make mistakes. Everybody's going to get things wrong sometimes. But if you don't figure it out and improve on that, well, that's the problem. Okay? Because that's how you grow. That's how you get better at it. All right? Any questions about that? Everybody understand how we got 5 significant digits for this one? Okay? You need more examples?
Yeah.
Well, we got 50 questions to go over, but I'll go as far as you want to go with this. Okay, write this one down. And let's see if we can figure out how many significant digits we have now. So if we're going to improve on what you know, then you need to write down this number, identify specifically which digits you think are significant, and then if you make a mistake, that's okay, but you need to write down then when you figure out what your mistake is, what the correct answer is and what your misunderstanding was so you can correct it. Does that make sense? That's the way you're going to get better at this, or the best way to get better at this. You can just listen. But guys, I hate to tell you, listening isn't the best way to learn. It's a good way to learn, but it's not the best way to learn. It's when you listen and you write it down and you talk about it and you discuss it. All those are parts of how you learn this stuff, okay? Reviewing at home, all those are ways to make it stronger, you know, more foundational in your head. Okay. So how many significant digits do we have here? Okay, Valerie, you asked me to go over this. How many significant digits do we have here?
3.
3. Why are these 2 digits over here not significant?
Those are trailing.
They are trailing zeros, okay? In a bit more complete answer, we really don't know if those should have been significant. And so we have to treat them like they're not, okay? It's possible that I meant for those to be significant, but I can't make them significant without doing something else to it. And there are 2 ways to show those zeros being significant, okay? So let's look at the formal rules first. Zeros between significant digits are significant, and zeros that follow a decimal place and a non-zero digit are significant. Well, these 2 zeros here follow a non-zero digit, but they have to also follow a decimal place to be significant. That makes sense? All right. Since they don't, we assume they're not. Now, using the informal rules, we say that trailing zeros are significant if there's a decimal place. Since there's no decimal place, those 2 zeros are not going to be significant. Got that? Anybody have any questions about that? All right. Now let's talk about how we can make those 2 zeros significant, that we want those zeros to be significant. There are 2 ways to do that. I can put a decimal place like that, but I cannot put an extra 0 after the decimal place because that would be lying about the precision of the measurement. Okay? we'd be saying there were, instead of this 5 significant digits, we'd be saying there were 6, and there aren't. We can also write it in scientific notation. Where I move the decimal place from here, 1, 2, 3, 4. Well, that would show actually that there are 3 significant digits. If I want to show 4, or I'm sorry, 5, I'd write it like this. Okay? Does that make sense? Questions? More examples?
No, I'm good.
We're good? All right, then let's talk about addition then. All right, so for addition and subtraction, the rules are the same. Okay? Addition and subtraction are actually the same operation. Subtraction is just adding a negative number. Okay? So it's really just addition. I mean, some mathematicians would tell you that anyway. So let's see, let's do let's add these together. Why don't you do that? See what answer you come up with, then I'll give you the correct answer for us to evaluate. Okay? Cassie, have you finished? Okay. Okay, Cassie. What is the correct final answer?
Is it 28.72?
It is not 28.72. Okay. So let's see if we can figure out how to get the correct final answer. Okay. We have empty slots here. There's this 3 and this 2 and this 1 are in the same column of data. I don't have them lined up very well, but that's what they are, because my decimal places are there. So between this 7 and that 4 there is an empty slot. I can't put zeros there, unlike what you've been taught to do probably in math classes, because that would be lying about the precision of this measurement. This measurement was only measured to the 10th place on a balance. So if I put a 0 there, I'm communicating to whoever's reading it that I measured it on a balance that measures to the 100th place, and I didn't. So I have to leave that either blank or put some other kind of placekeeper there. And I've been teaching you guys to put arrows. You don't have to put arrows, but you can't put zeros there, okay? You can put dots there. You can put bunny rabbits. I don't care, but no zeros, all right? So let's put that. I'm going to put arrows here just because it makes it easier to see what's going on. Then when I put the digits lined up under these the way they should be, 28.718, okay? And what she did was just to round this 1 up to a 2, and she failed to notice that there's an empty slot there as well, okay? So because there are 2 empty slots, both these digits have to be rounded off. Now, notice I put units of measurement and species next to every number. Okay, that's not part of significant digits, but I'm just reminding you while I'm here that is required. You cannot write down a number for me that's supposed to have a unit of measurement without writing the unit of measurement. You cannot write a number and a unit of measurement down that's supposed to have a species, where that unit of measurement and measurement apply to a specific thing. You have to show me or tell me what that specific thing is, okay? Got to be clear. And so we're going to write grams of NaCl here, all right? And now we're ready to round off. And the only mathematical operator, Lucas, that we're allowed to use in this class to show that we're rounding off is an arrow. It doesn't have to be a curved arrow. It can be a straight arrow, okay? And we're going to write out 28.7 grams of NaCl. Okay? For the record, since we're right here, this is not the best way to round, but it's the way you've been taught to round since, I don't know, whatever grade it was in elementary school when you first learned to round, where you learn to round up if the first digit you're rounding off is a 5 or above, and keep the number the same if the first digit to the right you're rounding off is below a 5. There's a better way to do that. We just don't learn that at this point in time. But when you get to college, you'll know there's a better way to do it. Okay? All right, we good with that? Do we want more practice, or are we okay with addition and subtraction? I don't. Okay? All right. Let's go to multiplication and division then. Since 99% of all the multiplication and division problems we do in a chemistry class is multiplying fractions, that's how I teach you about multiplication and division, okay? And so let's say I'm going to react hydrochloric acid with barium hydroxide. And I'm going to get water, and I'm going to get barium chloride. All right. I need an atom inventory. Whenever you're balancing chemical equations for me, you must have an atom inventory. 1 hydrogen here and 2 here for 3. 1 chlorine here, 1 barium here, 2 oxygens. On the other side, currently I have 2 hydrogens, 2 chlorines, 1 barium, and 1 oxygen. And what I want to try to do is arrange things so that I've got the same number of atoms on both sides. Once these formulas are balanced, and I've written balanced formulas, once the formulas are balanced, you've got to leave them alone. You can't touch the balanced formulas. Okay? The only thing we are allowed to do to balance an equation once the formulas are balanced is to use coefficients. And since I have an uneven number of hydrogens here and an even number of hydrogens here, I know I've got to change the coefficients somehow to get everything even. Okay, I can only have even numbers on this side because there's 2 in this formula. That's the only formula that has the hydrogen. The easy thing to do is to notice I hope you can notice this. You got 2 here, and if I put a 2 here, that'll balance out the number of allow me to balance out the number of hydrogens a lot more easily because it'll give me an even number. So by doing that, that's going to give me 4 hydrogens. It's also going to change the number of chlorines to 2. And if I put a coefficient of 2 here, changing the number of hydrogens and oxygens, I'll get 4 and 2 and everything's balanced. Let's see if if 3.50 grams of hydrochloric acid it was reacted with an excess of barium hydroxide. How many grams of water will be produced? No, let's say barium chloride. Now notice barium chloride over here is not a solid. Just for the record, we're not going to be able to filter out the water and get the barium chloride. we'd actually have to evaporate the water to get the barium chloride, assuming it goes to completion. But that's another way to collect a solid when it's not going to be forming a precipitate. Okay. So we're going to need molar mass for both hydrochloric acid and barium chloride. So these two right here we're going to need molar mass for. Hydrogen in an honors class, using the periodic table we use to get ready for AP chemistry, is 1.008. That's the atomic mass of that. Chlorine is 35.45. And I didn't line those digits up to be able to add them together the way that I probably ought to. I'll come back to that in a minute. Barium, I'm going to go and write that down, is 137.33. Chlorine, we said, is 34.45. Since we have more than one chlorine here, I've got to multiply. I'm going to line up the digits properly here for you. Alright, the way we're going to get molar mass is to add all of the masses of all the atoms in the formula and write the answer in units of grams. Okay, so this 34.45 plus 1.008 gives me 35.458. Even though I didn't line up the digits properly, there's an empty slot under that 8. Yeah, I made an error there, didn't I? Okay, 70. But here's the thing. 70.9. Your calculator shows 70.9. Okay? Why would it not be 70.9? Okay, if you were to add these two together, and that's what multiplication is. Multiplication is just another way to add things. If I were to add these two together, this together to itself, there would be no empty slot under the 5, or no empty slot here where the 5 is. And so it would be 90. And you have to be smart enough to know that your calculator doesn't handle significant digits very well. Okay? Yes? So I said it correctly, but I wrote it down wrong. 35.45 is the mass of chlorine. All right. So let's see. We got a 3, 12, 8, 10, 208.23, 35.458. Empty slot above. Okay, 36.458. And an empty slot above the 8, rounded off. This is grams of HCl here, 36.46 grams of HCl. And for me, in this class, you're required to write this as equal to 1 mole of HCl. We are getting to the multiplication division here in a minute, okay? Right now we're just doing addition, and I seem to be having trouble with addition for some reason this morning. So this is going to be grams of barium chloride, but there's no empty slots over here, so there's no reason to round this one off. And this is equal to 1 mole, and I can't even write today, barium chloride. Alright. Now, the reason that I have you write it in this form is because it makes it easier to set up the kind of calculations that we do, or the 90% of the kind of calculations we do in here. The reality is that the molar mass of hydrochloric acid is 36.46 grams per mole. But if you build a conversion unit from that, you will get grams per mole. Okay? You understand? And so this would be 208.23 grams per mole, the molar mass of barium chloride. We write it like this because it makes it easier for me to explain how you get a conversion unit to be able to do stoichiometry. All right? So that's what I want you doing here. After this class, hopefully you'll be able to handle it because you've done it so many times. That's the goal anyway. All right, now we're starting with 3.50 grams of hydrochloric acid for 99%, close to it anyway, of the math we do in here. You always put the starting amount over 1. That doesn't mean that's going to carry through after this class. We're almost at the final exam because this is final exam review. So you just got to know that for us, that's the way I told you to set it up. But you also need to know that there could be math problems in future classes where you won't set it up exactly like that. But that's the fallback position. I obviously recommend you always start with that if you don't really know where to start, because that almost always is going to get you going where you need to go. Okay? So we're going to put our starting amount over 1, 3.50 grams of HCl over 1. Okay? And we want to use this conversion unit to convert to moles. Now, or this equality statement to build a conversion unit to convert to moles. And we can do that by putting the side of this equality statement that matches these units and species, this side here, on the bottom of this fraction. The other side goes on the top. This is a conversion unit. A conversion unit is called a unit because it's 1. Okay? Since this equals this, we know that because we did it here. This equals this. The value of this fraction alone equals 1. So when I do this math here, I'm not changing the amount. I'm changing how it's measured. But the amount stays the same because I'm multiplying by 1. Now the next step, though, in stoichiometry then, is to build a molar ratio, which isn't a conversion unit because it doesn't really equal 1. But the molar ratio puts the number of moles of the starting species and the number of moles of the ending species you want for this problem in a fraction. We want to put the starting species down here on the bottom, 2 moles of HCl, because it's going to allow us to cancel moles. So let's go ahead and set up a canceling we're supposed to be doing here. We're going to cancel grams and HCl, just like X's and Y's in algebra. We're going to cancel moles, and that should be HCl, not HC, and HCl. Okay, and when we put the 1 mole of barium chloride on the top, if we were to stop and do the math at this point, we'd have moles of barium chloride. The thing is, we don't want to know how many moles. We want to know how many grams of barium chloride we need, and that's where this molar mass comes from, or is used for. All right, so here we're going to put moles of barium chloride on the bottom. This side of the equality statement here at the bottom goes down here. This side of the equality statement goes on the top. That allows us to cancel moles and barium chloride. And that's why we build our molar mass calculations this way, where you set up the mass equals a mole, because it allows us to build these conversion units effectively. All right, now we're ready to do the math. Or I heard some people getting out a calculator. If somebody already calculated this for me? No? Well, I heard the clicking sound of somebody opening a calculator. You did? Who did? Well, she's not speaking up. She's still working? Okay. All right, so the way that I taught you to do this is you multiply everything across the top. So 3.50 times 208.23, and then hit your equal sign. All right, and then hit divided by this number, divided by 36.46, and hit equals, and then divided by this number here. And that process is a fast way to get the answer for every calculator. It's not the only way, but every calculator will do it this way, and it kind of speeds things up for you. So I got 9.994583,105 grams of barium chloride. Finally, we can talk about rounding significant digits. Okay? We're going to look at the measured and calculated numbers in the problem. This is a measured number here. It was measured to find the grams. This was calculated. We know it's calculated because we calculated it. This was calculated. Okay? This was not calculated in the same sense. Okay? This is actually counting up here, not so much calculating. All right? So we're counting the number of water molecules or the number of hydrochloric acid molecules, and not, well, we are calculating it, but it's more of a counting. It's a counting number as opposed to a calculated number. Okay? So we're not going to use this number or any of the ones. We're only going to use these I've highlighted for figuring out significant digits. And we want to figure out which one of these these measured or calculated numbers has the least digits. This one has the least digits. It has 3. This one has 4, and this one has 5. So we want our final answer to have the same number of digits as the measured or calculated number in the problem with the least digits. 1, 2, 3. We're going to count 1, 2, 3. Underline everything else. Draw an arrow, because that's the way that we designate insignificant digits with the underlining, and the only operator that can be used and must be used to show rounding. So 9.99 grams of barium chloride is our final answer for this problem. Have I covered significant digits for you adequately? Any other questions about significant digits?